After discussing the equation of a plane, we want to look at how two or more planes interact with each other. So this will be split into two parts. The first part will only discuss two planes, and then the second part will look at three planes. So what happens when I have two planes? Well, there are only two or technically three situations. One is that the planes are parallel, and in the case that they're parallel, sometimes you actually get the same plane, so they coincide. So we're still under this idea that they're parallel, or they intersect at one line. So you can see this green line that goes through both planes. This is the line of intersection. So just like the idea of lines intersecting at a point, two planes will intersect at a line, not at a point. So two planes are parallel, their normal are collinear. Otherwise, they intersect at a line. So it's much easier to check for parallel first, and then look at whether they intersect at a line. The algebra behind this is not new, but we just need to adapt it a bit to planes. And this line, just to clarify, if they are parallel, then the normal of the planes will be collinear, so they will lie on the same line. So just to clarify again, if I am given two lines in here, so two planes, plane 1 and plane 2, and where they have the normal vectors n1 and n2, then we have they will intersect into a line, and there are three ways to prove that. First of all, you can find two common points, and therefore you can write it as an equation of a line. Go back to this lesson on equation of a line, and or they would have one common point, and then you can find the direction vector by taking, if you have the normal vectors, you can take the cross product of the normal vector, and that will be the direction vector of your the line that they intersect in. Or another method to find this intersection line is to actually solve the equation like a simultaneous equation. So I'll be looking into this method because these are simple to do. Then if two lines are parallel, you just need to check if their normals are parallel. And then if they coincide, you first check that they are parallel, and also that one equation is completely a multiple of the other equation. So we'll have a look at how to show that. So if I have this, so I have three planes, plane 1, plane 2, and plane 3. We tend to denote plane with a pi, either a lowercase or an uppercase. So I need to show that plane 2 and plane 3 are parallel. So how would I show that? I'm just going to do it here because I'll need space for part B here. Well, first of all, I can take the normal of plane 1 and show that it's a multiple of plane 2. So the normal of plane 1, so the normal of plane 2 is 1, 2, and -1. Remember, you take the coefficients of your x, y, and z. That will be the normal. And n3 is just 2, 4, -2, which is the same thing as saying 2 multiplied by 1, 2 minus 1, which is the same thing as saying 2 times the normal of the second plane. So I have shown that they are parallel. So I know that they are parallel. Now, what if they coincide? What if they are the same line? Well, here's how you can check. If I'm saying that the third plane is double the second plane, so what if I double all of the second plane? So n of the second plane will give me 2x plus 4y minus 2z equals to 0. This is close to the third plane, except that on the other side it's not 0. So it's not equal to the third plane, so they do not coincide. So they're not the same plane, they're just parallel. So that's completely how you show that they are only parallel. So make sure that you completely answer the question. So you need both parts. If it just said if it said coincide, so you immediately know that you have to go all the way there. If it says parallel, you still have to show that other part. Now for part B, you need to show that plane 1 and 2 intersect. You can show from the beginning that they are not multiples of each other. So show that the normals are not multiples. Show they are not parallel. I'm not gonna go through that. You can just show that you cannot take, it's not a multiple of each other, just pointing it out. So then if they're not parallel, then immediately the only other possible situation is that they intersect. So you don't have any third option in here. So if they intersect, it means we need to solve the simultaneous equation. So remember, the different ways you can solve this is you find two common points and then you can find the line, or you have one common point and then you find the direction vector. We can find the direction vector, but finding a common point is a bit tricky since you don't know where to start with a common point in both planes. There are infinitely many points on both planes, so it's a bit hard to get to the right one. So we're going to solve the equation simultaneously, and what we're trying to get to is a like a parametric representation of the plane. So it will make sense as we go along, but we're trying to represent every letter, so every x, y, and z with reference to one letter. It's not making sense now, but let's start to solve it. The process is not too unusual. There's something similar that is done when you have a system of 3 equations, but now you only have 2 equations here. So what you want to do is you want to eliminate one letter at a time until you get down to one letter. That's one method to solve this. So we will try and eliminate the x first and then the y, so we get something in terms of z everywhere, and we represent x and y in terms of z. Now this is arbitrary. You can represent the letters in terms of y, you can represent the letters in terms of x. You will get slightly different looking equations, but they all represent the same equation of a line, the intersection. So let's start with, I'm just thinking of eliminating the x, so I will double the second equation and I will subtract the 2 equations from each other. So I get 2x minus 3y plus 5z, and then I have 2x plus 4y minus 2z equals to 0. I'm going to subtract these 2, and I end up canceling the z, which is what I wanted, so I end up with negative 7y plus 7z equals to 1. So I've eliminated the x, I have this equation, and what I'm going to do is I'm going to now represent y in terms of z. And again, here you could do the opposite. You can represent z in terms of y, but the idea is to get one letter to be the representative of the other letters. So in this case, I can then say that y is equal to z minus 1 over 7 if I simplify this. Now what we're gonna do is replace this in, let's say, one of these 2, and I'm gonna pick the second one because it's easier, and I'm gonna end up representing x in terms of z only. So I have x plus 2, whatever my y was, minus z equals to 0. And then when I simplify this, I end up with x equals to negative z plus 2 over 7. Now, what we did so far is that x is, let me put the numbers first, you'll know why. 2 over 7 minus z. Y is negative 1 over 7 plus z, and z is just z. And this is what we got to. So we're representing all the other letters in terms of z. And again, you could have eliminated the y first or the z first. You could have made a z the subject instead. So the idea is that at least one letter will be itself, and then the two other letters will be represented by that letter. But we don't want to just have this letter in there. What we actually want to is to represent z with a parameter. So we say that z is actually alpha, and so y is negative 1 over 7 plus alpha, and x is 2 over 7 minus alpha. So now we have the equation of a line in parametric form. Okay, so the equation of a line is dependent on the value of z in this situation. And you can rewrite this line in any other method. You can write it in Cartesian form, for example, where you make lambda the subject. So in this case, we will get, let's start with vector form. So you end up with the values are going to be, so 2 over 7, negative 1 over 7, and 0 for the z, plus alpha, you get minus 1, 1, and 1. So this is actually a point on the line, and this is the direction vector of the line. And then from there you can represent it using using Cartesian form as well. The book, if you have access to the book, this is taken from the IB Oxford book, and they do it, the first method they actually make x the lambda, and then they represent everything else. They get a slightly different equation in Cartesian form, so they end up with something. They end up with a Cartesian form in there, but the idea is if I replace this point that I found in the Cartesian form that they have, it will still give me the correct answer. It will give me that this is a correct point on the line that they found. So this is where we say, yes, there is a unique line. However, the representation of the line is not unique. You can have different representations for it. So just to clarify on this. So the Cartesian form that they have is x equals to x over 1, y minus 1 over 7 over minus 1, and z minus 2 over 7 over minus 1. So notice how their normal vector 1 minus 1 minus 1 is just the negation of what we have, and the numerators are slightly different. But if I replace the points that we found here, or you try and solve it for each one will give you a lambda equal to 2 over 7. So it's correct. It will just show you that your point fits on the line. I'm gonna just quickly on the side explain what I'm talking about, but you don't need to listen to this part. So what I'm talking about is this is our line, and this is another method where it's not z that's the lambda as we did here, it's x that's the lambda. But just to prove that these two are still representative of the same line, you can solve this you can replace basically 2 over 7 with the points. So 2 over 7 instead of x will just give you 2 over 7. Remember that all of these are equal to lambda. So it's telling me that if you want 2 over 7, then your lambda has to be 2 over 7. Well, that's for the x. Let's check for the y. If I substitute negative 1 over 7 for y, and that's negative 1 over 7 again, over negative 1, that will give me a negative 2 over 7 over negative 1, which is 2 over 7. So again, it's telling me lambda has to be 2 over 7 for you to get this y. And then I can do it for z as well, where it's 0. 0 minus 2 over 7 is just 2 over 7, sorry, negative 2 over 7 over negative 1, there's no space, which is just 2 over 7. So notice how they're all giving me a 2 over 7, 2 over 7, 2 over 7. So there exists a single lambda, 2 over 7, for this equation that will give me this point. So this point does lie on the line. So I'm just proving that these two are similar. So that's how you show that two lines intersect, and you find the equation of the line. That's one form to find the equation of the line. Now, if you have a GDC, you can also do that on the GDC. You go to simultaneous equation solver. You go to the polysimultaneous app in the apps section. You go to the simultaneous equation solver, and then you pick two equations, but you have 3 unknowns. So just keep that in mind. Then we'll go to next. You put in your coefficients as normal. So I did for the first equation, my second equation, and then when you solve it, notice what happens. The calculator takes z, so this is x, y, and z. So your z as the lambda, and then negative 1 over 7 plus z, and then 2 over 7 minus z. So the same thing that we got. So that's a good way to check your solution if you need to. All right, one more example on this. So if I have 2 planes, I need to determine if they're parallel, if they intersect at a line, or they coincide. So the easiest thing to do is first check that they are parallel. So first we take the, let's name them plane 1 and plane 2. So the normal for plane 1 is just 1, 2, and 3. And the normal for plane 2 is just 2, 4, and 6. And I can show that if I double 1, 2, and 3, which is the normal for the first one, it will give me the normal for the second one. So this is double and 1. So I can safely say that they are at least parallel. Now this is one way to prove. You can do a slightly different algebra work or something, but you have to show there's a doubling somehow. Now, I've shown that they're parallel, which means they don't intersect at a line, so they are parallel, but do they coincide? Let's check. Well, if I'm saying that it's double the normal, well, let's take double the first plane. That will give me 2x plus 4y plus 6z equals to 20, which is exactly the same as plane 2. So because one plane is a multiple of another, we say that the 2 planes coincide. Okay, so first you've shown that they're parallel, and then that one is a multiple of the other. And that's it for 2 planes. So we've shown all 3 different scenarios. For 3 planes, it's going to be a slight extension from what we've done, but for 3 planes we go back to something familiar, what you've done in system of 3 equations.